In this video, I'll use a cheap wireless doorbell and hack it so it sends me a push notification when someone's at the door. That's why we'll open it up, take a closer look inside and figure out how it works. Then we'll find out how we can hook up a microcontroller, which then sends the doorbell event via Bluetooth. We'll also take a look at how such things are connected in general and how you can set up your very own Things network. So let's open up this unit and take a closer look under the hood. At a first glance we can see that there's not so much on the upper side of the PCB. There's the mains coming in on the upper left corner and 3 LEDs on the right side. It also seems that they have used a pre-manufactured board for the wireless communication. It features a PT4303 chip, which is a low-power wireless receiver circuit that was configured for the 433 MHz band. That only has 4 pins, so 2 of them might be for the power supply and the 2 other ones could be transporting a serial bus. This may be a good spot for hooking up our controller, but let's first take a look at the bottom side. Here we have a simple power supply circuit on the right side that features a bridge rectifier and 9V Zener diode providing the input voltage for a standard LM78L05 5V linear regulator. On the left side we have 2 ICs without any part numbers. The left one is presumably the one with the main logic. Since the speaker is directly connected to the right IC, I assume it is a dedicated audio chip including an amplifier circuit as well as a flash storage for holding the chimes. Aside from that, a little MOSFET or transistor is used to drive the LEDs. That's basically it, pretty simple. So let's find a nice spot on the PCB to which we can hook up to. Of course I'm not poking around here while this thing is live and you shouldn't also, so I hooked up my lab power supply to feed in 5V. My initial thought was to hook into the data that comes out of the wireless module. I took my Rigol DS1054, switched it to roll mode and poked around while pressing the doorbell. But after a couple of minutes I kinda figured that I could utilize the internal circuit that already processes data coming from the RF module. I mean, the LEDs start blinking when somebody rings the bell, so my Arduino could simply use an interrupt on one of those pins to detect that. And that's basically what I ended up doing. I searched for the pin that is outputting the signal for the LED driver and soldered in an access wire. This will later be used for the Arduino to detect that someone has pressed the doorbell. So, sounds good in theory. Let's put together a simple prototype and give it a try. In my Logic Stuff organizer box, I searched for an appropriate module. I do have a couple of RFduinos that are pretty small and already have Bluetooth Low Energy built in. Luckily, I also have 2 modules pre-soldered on a prototyping board that fit into a standard breadboard. Well, keep in mind that the RFduino is way too expensive nowadays. I already have mine for a couple of years now. Today I'd rather stick with something else like an AdTiny85 in combination with a cheap Bluetooth bridge or even an NRF24 L01 module. But yeah, I have a couple of spares, so I use them in this project anyway. So let's create a new Arduino project. To ensure everything is working fine, I've just written some boilerplate code to enable the LED. So, before we continue writing code, there's one problem we need to take care of. The Arduino runs at 3.3V, while the logic level of the doorbell is at 5. So I've soldered in 2 wires that connect to the 5V rail of the board and hooked up a small buck converter to step down the voltage. Never forget to add a smoothing capacitor to those cheap step-down regulators from Banggood, AliExpress, eBay or whatever. They have a ridiculous amount of output ripple that you don't want in your microcontroller circuit, especially not if you are dealing with RF modules. They tend to be very sensitive to any power-related issue. We also need to convert a 5V LED signal. For that we use a simple voltage divider based on a 1K and a 2.2K resistor. Now we should be pretty much done with the prototyping electronics. Back on our desktop I've already updated the previous Arduino code. First I added a new pin that represents the signal input. Remember, this signal is actually the LED signal that blinks when it gets triggered. It is low if nothing happens and will go high once somebody's at the door pressing the button. So in the setup function I've set this pin as an input, initially turned the status LED off and started the Arduino Bluetooth LE stack. The interesting part is within the loop function. Here I utilized the pin wake and power down methods that were provided by the Arduino library. So what you can do here is define a pin that wakes up the Arduino from a deep sleeping state. Since our signal is rising from low to high, this is a perfect scenario for such a wake up call. So after we've enabled the ultra low power mode, we go into a while loop that will only exit once that specific signal pin gets high, so when somebody actually presses the doorbell. Once that is the case, we simply send something via Bluetooth and turn on the status LED. Now, since the LEDs of the doorbell are blinking instead of just turning on, we need to add a delay to ensure it only gets triggered once and not many times while the LEDs are blinking. To make sure the data is fully transmitted before we delay the whole processor, the radioactive property of the Arduino BLE class comes in handy. We wait for that to be finished and then start a delay. After transmitting and waiting 5 seconds, we simply turn off the status LED and re-enable the wake up pin. Then everything will start over again until somebody presses the button at the door. So actually the code for the Arduino side is complete. Let's compile and upload that and then press the doorbell button. Sure enough, at least our status LED turns on. To also test if something got transmitted, I used the free Lightblue app from the Mac App Store. There are pretty much endless free tools like that for any operating system available. Just pick the right one for you. After selecting the doorbell device and subscribing to the right characteristic, we can see our sent packet. Awesome. So how will we proceed from here? We got all our Arduino stuff ready, but how will this send a push notification? It's now time to think about the whole structure of the project. Well, let's think a minute about how things might be connected. In our example, we have a device that communicates via Bluetooth. Next time we might prefer Wi-Fi or something like the NRF modules or even a tethered 2-wire communication bus. So how can we consolidate all those individual endpoints and create applications like in our case sending a push notification once something happens? The key here is to think about endpoints like our doorbell trigger in a very modular way. That means every endpoint has its own single responsibility. So the doorbell cannot and must not know about any other device in the system. Its only purpose is to tell the system that somebody is at the door and has pressed the button. But who actually sends the push notification? First we need some kind of centralized hub that can send and receive messages from and to any endpoint. It is responsible for the communication method and type, such as Bluetooth, Wi-Fi and so on, as well as for exposing a centralized API to which our apps can hook up to. These then only connect to that hub, not to the individual module anymore. That makes it very powerful because the apps do not need to know any technical detail in how to actually connect to an endpoint, and because every app can have access to any endpoint in the system. So with this method we can create an unlimited number of endpoints as well as apps that gather information from them and create awesome stuff with that. Another great example would be a battery charger endpoint and a second app that can send you a message once your batteries are fully charged. So there are billions of possibilities to create awesome apps that interact with the world of sensors, motors, 3D printers and whatever you can imagine. Alright, so let's get a bit technical. How do we actually make our Arduino do something in this connected universe? And how do we actually send a push notification? Well, this leads us to a protocol called MQTT. This is a system that is based on a publish and subscribe model. All endpoints and apps are connected to the hub, which is also called the MQTT broker. Every single endpoint has its own unique address that looks like an URL. Think of the URL path like a location where the endpoint physically sits. I'm in my office and the doorbell belongs to that office. So my URL could be something like /office/doorbell or /office/door/bell. The latter one would be nice if we, for example, add a door camera at some point in time. That would then, for example, be addressed as /office/door and then /camera. You can basically call it whatever you like. I'll stick to /office/door/bell because I find it a lot cleaner. Also, every endpoint like our doorbell or battery charger has certain capabilities that it wants to expose to the world. These capabilities are called topics. Think of the real physical features that a particular endpoint has. They could be exposed as topics. So in our case, our doorbell just has one topic that we might simply call button. If we, for example, would implement a feature that allows us to switch the ringtone, we could also add another topic called ringtone. I think you know what I mean. The topics simply are appended to the endpoint's address. So in our case it's /office/door/bell and then /button. Since our endpoint only has one capability, we can simply use the endpoint's address to publish to instead of defining a topic. In general, the terms endpoint and topic are technically speaking the same thing. MQTT only has these addresses that you can publish to. Calling it an endpoint or a topic is just a way to ease up things. So again, I'll stick to /office/door/bell. Now all the doorbell has to do once a person presses the button is to publish a message to its specific topic. It could, for example, just be the string pressed. This will be received by the hub and distributed to all apps that have subscribed to that topic. This of course would also go the other way around. Let's say we've implemented the ringtone topic. so the doorbell would rather subscribe to that topic and wait for a command to come in instead of publishing something. The useful thing here is that you could have basically unlimited apps that subscribe to a single topic. Every one of them will receive the same message. Now, there's a last little note before we continue to implement all of this in a real-world scenario. It's absolutely possible to implement this within 3 different devices. The broker could, for example, be a Raspberry Pi. The app could run on an iPhone, and the doorbell could be an embedded Linux device. However, you could also put all of these in a single Raspberry Pi. The broker is basically just a background web server that is running at port 1833. The app as well as the doorbell could be implemented as 2 separate instances of a Node.js application. There you could simply connect the button to the GPIO pins of the Raspberry Pi, make the Node.js app wait for a button press and then publish it to a locally running MQTT broker. The app would locally subscribe to that topic and then perform the push notification. We, however, will use something pretty similar to that. Because our Arduino doorbell is pretty limited in its processing power, I'd rather not install an MQTT client just to publish a single string. Instead it will, and like we already implemented, simply send a message via Bluetooth, which then will be received by a Node.js app that is running on the Raspberry Pi. You can consider these 2 objects as the single doorbell endpoint, even though they are physically 2 separate things. You can do that because the combination of the Arduino and its companion Node.js app will be responsible for subscribing and publishing topics for the doorbell endpoint. Our push notification service, which will also be made with Node.js, will then subscribe and call a public API to perform the actual push notification. So that's basically it. Congratulations if you have made it to this point and are still watching. We will now continue installing the MQTT broker on the Raspberry Pi and writing the companion Node app for the Arduino as well as the actual push notification service. Even though the theory sounds complicated, you will be surprised on how fast we actually get the end result and how little coding work needs to be done. We will now prepare our very own private IoT environment that will be reused by many following projects. I will not go into the details of setting up your Raspberry Pi. There are so many great tutorials that do just that. Make sure your Pi is turned on and then connect via SSH. Copy the IP address, go to your terminal and connect with your Raspberry Pi user. Type in your password and then you are ready to go. Well, the first thing before installing new stuff is to always update the package manager. After that, you can install an MQTT broker called Mosquito. This single command is everything you have to do. That's it, it's running. Now, that command also installed a client called Mosquito Sub. We'll use that to test our doorbell endpoint and its topic. Run it to subscribe and wait for any message coming in. Back on our desktop, we can launch a tool called MQTT.fx. Which is also an MQTT client but with a graphical user interface. Open up the settings and add your Raspberry Pi as a new connection profile. Type in its address and leave the standard MQTT port. Type in the topic to which you'd like to publish to and write your very first MQTT message. Back in our terminal, we sure enough see that this message has found its way to our broker. Awesome. Now, as you might have noticed, we didn't set up any configuration file or something like that, which kinda defines our endpoints or topics. If you publish to a topic that not yet has existed, it will be simply created. Another great reason to use MQTT, it's that simple. What we have done so far is completed the setup of the Raspberry Pi. The MQTT broker is always running as a background task. It is accessible through the Raspberry Pi's IP address. Let's continue with the companion app that receives Bluetooth messages from the Arduino. Now, because I want to write code on my local machine and not on my Raspberry Pi, I'll create a new folder on my desktop, set up a Git repository and initialize a new npm package.json file. To begin, we need an MQTT library. We install it through npm and save it to the package.json. After opening the project folder, I've created an index file which will then hold the entire app. I've written some basic code to publish to the doorbell topic. You can see how simple it is to use MQTT here in JavaScript. Just create a new MQTT instance by requiring the library. After connecting, we are already able to publish text to any topic we like. Alright, so now let's implement our Bluetooth stuff and then only publish that message when the button actually got pressed. For that, we'll require a second library called nobile and also save it to our package.json. I've already updated the code off camera and will now just jump ahead to the important stuff. You can always take a closer look at this code on GitHub. We search for a Bluetooth device named Doorbell and then connect to it. Then we subscribe to that and wait for the data event to occur. This is the callback that will be triggered once the Arduino actually sends the button pressed command. Here's the appropriate spot to publish the message to our broker. By calling node index.js, we give it a first run. Alright, so that looks fine. Now let's head over to the desktop and create our push notification app. This will be that simple since it is just subscribing to the doorbell topic, and once something happens, shoots out a notification to our phone. On my local machine, I've already created a new folder called push notifier, initialized the Git repository and added the package.json. For the push service, I've chosen a tool called pushover. Sadly, it only features a 1-week trial and then requires you to do an in-app purchase. Maybe I'll create a free service like that in a future video. Who knows? I am not sponsored or affiliated by pushover in any kind. Yes, you can use whatever tool you like, but I find pushover pretty simple to use. Go to their website, create a new account and then create a new app. In my console, I've npm installed the pushover library as well as the MQTT client, saved both to the package.json and already finished the index.js file. It's pretty straightforward. First I created an MQTT client like we did before. Then I created a pushover instance and pasted in my API key as well as the user key. You can find both of them on the pushover website. And yes, you can try, but at the time where you are seeing this, I've of course already generated new keys. So after that, I subscribe to the topic, and once a message comes in, it sends a push notification to the pushover service. That's it. I've downloaded the official pushover app for iOS and logged in with the same account. After starting the push notifier with Node and hitting the doorbell, I do get my notification on my phone. Now that we have both apps ready, we can push them to GitHub and finally install them on the Raspberry Pi. But before we do that, here's a quick hint. Of course, you don't want to publish any credentials to a public repository. You can take care of that by creating a new file called credentials.js. Copy your credentials object and paste it into that file. Then require it in your main code and simply pass it to the pushover object. Now simply ignore that file by adding it to the git ignore and you're done. This way everyone that pulls your code has to first create a new credentials file without ever seeing yours. So since we are finished, it's now a good time to commit and push both apps. I've created 2 new public repositories on GitHub, added those as remotes and pushed the master branches. So what have we done so far? Right at the beginning of the video, we've created the actual Arduino code that is running on the Arduino. It sends a simple Bluetooth message once it detects the button has been pressed. Then we've set up a simple Node.js app that is able to receive that Bluetooth message and publishes it to the MQTT broker. These 2 parts together form the actual doorbell endpoint. Then we've created a second Node.js app that just subscribes to the doorbell endpoint and waits until a message gets published. Once that happens, it sends a push notification via pushover. Great, now these apps still run on my local machine. Before we can run them on the Pi, we first need to do some initial setup to make the Bluetooth stack work. I have a Raspberry Pi 3, so the following will be suitable for my version. If you have a different one, simply do a search on the internet on how to set up the Bluetooth stack for your Raspberry Pi. Back in our SSH console, we first install a couple of tools via apt-get. Then of course we need Node.js. By pasting in this command, a more recent version of Node.js will be added to the package manager. After that, simply install and then check the Node.js version to make sure everything is working fine. At the time of this recording, it is at 7.5. Perfect. So still on my Pi, I create 2 new folders in my home directory. One is called endpoints. This will hold all the MQTT endpoints in the future, including the doorbell one from today. The other one will be called apps. Here we put in our IoT apps like the push notifier. So let's go into that endpoints directory and clone our recently published Arduino doorbell repository. Then cd into that, run npm install and run it with sudo node index.js. Well, the sudo thing here is a bit scary. The Bluetooth interface requires root to be accessed. To be able to run the noble library without requiring root, just execute the following command and try it again without sudo. Looks fine. So let's go back to the home directory and then go into the apps folder. We can now clone the second app, cd into it and also run npm install. Now we need to create the credentials file first. Remember, we did exclude that from the versioning system due to security. Paste in your credentials and save the file. Give it a quick test run if everything is working fine. Nice, we've installed everything, made sure Bluetooth is working and connected our Arduino to the Internet of Things. Now, we still have a problem. Currently we would have to open up 2 SSH sessions and manually start both Node.js apps. It will then work until we close the SSH channels or one of our apps gets closed. Additionally, if our Pi needs a restart, our apps will go offline as well. And that's not really what we want. It should rather run as unattended as possible. For things like that, there's a really handy process manager for Node.js apps available. It's called PM2. If you have time, you should definitely go through the documentation. This thing is absolutely amazing. But let's keep things short, as we already covered way too many topics here in this video. On our Pi, we simply install PM2 globally via sudo npm. Now, instead of running our apps with the Node command line tool, we now say PM2 start index.js. That's it. It is now running in the background instead of blocking our SSH session. You can always get an overview of all running apps by simply typing PM2 list. You can even take it one step further and launch the PM2 monitor. Here you get a crazy amount of stats for all your apps, but that's way too far into it now. To make sure PM2 will start and run our apps once the Raspberry Pi boots, we hit the command PM2 startup. But it tells us that we have to run that as root. So copy and execute the above command, and this has to only be done once. So as you can see, the running app is just named index. That's not very helpful once you have more than one app. To rename it, we first stop it by typing PM2 stop and then the process ID, which is 0. Start it again by appending a name parameter. As you can see, we now have 2 apps in our process list. That's because stop only stops, but not deletes the app. You could continue its execution later on. To remove it entirely, run PM2 delete 0. We now have a clean list of running apps. cd into the other Node app and also start it with a more appropriate name. Alright, by hitting PM2 save, the current process list will be stored on disk. Once the Raspberry Pi restarts, that stored list will be re-executed. We do now have a fully working Raspberry Pi that automatically starts and restarts our Node apps. I've just made another slight modification to the Arduino Doorbell code. It now automatically starts scanning again if it loses the connection to the Bluetooth device. This may be the case if our doorbell loses power, while we may putting it into a different mains outlet. If you change your code and need to restart a certain Node app, simply run PM2 reload all or PM2 reload and then the name of the app. So actually we are done now, but do you really want to plug that into your mains? Well, I don't. So I thought about a little backpack that fits onto the existing case and holds the Arduino. After soldering everything on a little PCB, I've designed that case in Fusion 360 and printed it out on my 3D printer. I glued the buck converter to the inside of the original case and put everything back together. With everything back in place, this project is finally done. I really hope you had a great time watching this video. If not, please let me know why. If you have trouble following along, you can ask anything in the comments. Links to the interesting stuff of this video will be in the description. Happy hacking, and I'll see you next time.